In this example, you're given a scenario where you're essentially gambling and you're asked, what should the cost of this game be in order for the game to be fair? So the idea of fairness in a game like this involving probability is what they're really asking for is what would you have to do so that the expected value of your random variable is equal to 0. So let's begin by first just understanding the mechanism of the game itself. So it says you reach into a jar of money, that sounds great, and you select a single bill at random to keep. There are 10 $5 bills, 7 $10 bills, and two $20 bills. So if you look at your $5 bills, see if we can kind of sort of draw this. So you have your fives. There are 10 of these. And then you also have a bill. You have your $10 bills. You have 7 of those. And then you also have 20s, and we have 2 of those. So you have this jar and you have 19 bills altogether, right? So your bills, you have 10 plus 7 is 2, you have 19 bills. So the probability of grabbing a $5 bill is equal to 10 out of 19, right? Because there's 10 $5 bills and there's 19 bills in total. So then similarly, the probability of getting a $10 bill when you grab a bill out is going to be 7 out of 19. And then your probability of getting a $20 bill is going to be equal to 2 over 19. So this is just basic probability. We haven't really talked about expected value yet or fairness. So what we need to do is we need to figure out how can we use these probabilities to determine the fairness of a game. Well, there's this thing that we haven't talked about, which is that no one's going to let you grab a bill for free, right? The idea is that you have to pay the game runner, the MC, whatever. You have to pay them a certain amount of money in order just to stick your hand in the jar and grab a single bill, right? So like, let's look at an example. Like, let's say it cost $1 to play, meaning you give the host $1, you get to grab $1 out. Now, if you think about this intuitively, that's a bad setup for the person running the game, right? Because the smallest amount of money you're going to pull out in terms of a bill is going to be a 5. So like if someone said like, hey, come pull a bill out of my jar, the smallest denomination is $5. Hey, it only cost $1 to play. I mean, I would do this all day until the jar was empty. I know I'm going to win at least $4. But let's just see what that looks like, right? So I'm going to put together a little table and we'll look at what the outcomes are going to be for each scenario, 5, 10, and 20. All right, so our table would look something like this. We want to record what our outcomes are. So remember that our outcomes are going to be based on what bill we pull. So you want to think of it as like your total winnings. So if it costs $1 to play, let's say you get a 5. So like, I'm going to say this is like you grab out a $5 bill. If it costs you $1 to play, that means that you're actually winning $4, right? If you grab out a $10 bill, then it costs $1 to play, but so you're winning $9. And then similarly, if you get a $20 bill, you've already paid that $1, but now you get a 20 back, so you've made $19. And so what you want to do is we want to pair these up with their probability. So what's the probability of winning $4? That's the same thing as the probability of pulling out a 5. So we know that this probability was 10 over 19. We know that the probability of getting a 10, which is the same thing as winning $9, was 7 out of 19. And then we had also 2 out of 19. So now what you want to do with this is you want to multiply these together. So you're going to have 4 times 10 over 19. You're going to have 9 times 7 over 19. And then you're going to have 19 times 2 over 19. And if you add these all up, then you're going to get your expected value of your random variable x. So your random variable x is your winnings. So let's actually keep that in mind at the top. That's going to be the same for all of these things. You could also lose money, right? So like, let's say we'll do another example where it costs $10 to play, and we'll see how that gets affected. So let's take a minute. I'm going to add these up really quick, and then we'll see what our expected value is. All right, so I just took 4 times 10 over 19. So I get 40 over 19 for my first x times px, and I do that for each 3 scenarios. For the expected value, capital E of capital X, meaning the expected value of our random variable, the expected amount that we think we are going to win or lose if we play this game a lot over and over again, is going to be 141 over 19. And so if you think about this, $141 over 19, that's approximately $742. That should make sense because we know it costs $1 to play. The smallest amount, the smallest bill we could pull out every time we play is a 5. So every time we play, we're going to win money. And we know that 4 is the smallest amount we can win on a single pull, and 19 is the biggest. There are a lot more $5 bills. So there's a lot more chance of us winning $4 than there is of us winning $19 by pulling out a $20 bill. So that's why it's bigger than $4, but just a little bit, you know, like if this was closer to $19, we would expect there to be a lot more $20 bills in there. But in any case, think about it. If you're running a booth and you're trying to like hustle people for money, you don't want to charge them $1 to play this game because everyone's a winner. So let's actually take this over to Excel and let's play with a little bit of other cost of pulling out a bill and seeing how it's going to affect our random variable. So in this Chapter 4 Excel template, I'm on the tab where it says mean and standard deviation from PDF. I don't necessarily need the standard deviation to answer this question, but I do want to compute the mean. So remember that the mean is the same thing as your expected value when you're working with a probability distribution. So at the bottom, we have mu equals sum of x by px. So this is the same thing as our expected value. Mean equals expected value. All right, so let's talk about our probabilities, right? So we know that I have 10 over 19. This would be if I pull out a $5 bill. Notice that when I put in a fraction, Excel automatically converts it to a decimal. This is totally fine. Excel is really good at rounding. So you don't even have to worry about that, which is awesome. So I put in 7 over 19, boom, and then I'm going to put in 2 over 19. The other thing that Excel does for us here at the bottom is that it tells us what the sum of our probabilities is. So remember that for a probability distribution, it has to add up to 1. So if for some reason your sum isn't 1, something's gone wrong. So you want to recheck your probabilities. Okay, So now we can kind of get into fun. So let's say it cost $10 to play this game. Let's say it costs $10 to play this game. So how would that change our outcomes? Well, let's look at the first case. If I pull out a $5 bill, I paid $10, I get $5 back, so I'm in the hole $5. I've lost $5 if I pull out a $5 bill. If I pay $10 and I pull out a $10 bill, I broke even. I didn't win or lose anything, so I get 0. If I pay $10 and I get a 20 out of it, cool, I just made $10. So that's how I get my X values here. And so now what's happening is if we look at this, if I were to pay $10, look at the mean. The mean is negative 1.57895. So what does this mean? Pun intended, I guess. The expected value or the mean, right? So remember that this is the same. This is your expected value. X, right? It's negative. So now what I'm doing is I'm expecting to lose $1.58 every time I play. So in the first example, I was expecting to win $7.42 every time I played. That was awesome. This time it's costing me more to play. So I actually have a risk of losing money now. And my expected value is negative 1.578, whatever. So, okay. In the beginning of this problem, we said, we want to figure out, well, how much money can what do I have to charge in order to make this a fair game? So there's a couple things you could do. You could play around a little bit, but you could also look at this algebraically. So if you think about it, let's get another table. Let me set it up. Movie magic, hold tight. All right, so what should it cost if we want to make it a fair game? Well, right now we don't know. It's definitely somewhere between $1 and $10, right? So when it was $1, we were winning too much. When it was $10, we were losing too much. So it's probably closer to 10, but just a bit shy. So let's just call it Z. Let's say it's Z dollars. So then if I get a $5 bill, then my winnings would be 5 minus Z, right? Because like the first example, when we charged $1, it was $5 minus what we charged, $5 minus $1. So our winnings was $4. When we pulled out the $10 bill, our winnings were $9 because it was that 10 that we just grabbed minus the cost of playing the game, which was $1, right? That was the first example. And then in the second example, when it was $10 to play, right? If we grabbed a $5 bill out of the jar, but we cost $10, well, 5 minus 10, that's what gave us that negative 5. So I'm going to do this for each one. So 5 minus Z, 10 minus Z, 20 minus Z. And now for my X times my P of X, now this is where it gets a little bit tricky, because what's going to happen here is that you have to be really careful with your algebra. So this is going to be 5 minus Z in parentheses times 10 over 19. And then this is going to be 10 minus Z times 7 over 19. And then lastly, I'm going to have 20 minus Z times 2 over 19. And our expected value, right? Remember that mu or mean is the same as our expected value in this case. This is going to be 5 minus Z times 10 over 19 plus 10 minus Z times 7 over 19 plus 20 minus Z times 2 over 19, right? So this is just our outcome times the probability. We're not really used to seeing variables in our outcome, but when you want to figure out how to make it a fair game, you have to just accept that you don't know what to charge right now. That's why the Z is there. So now let's work through our little PEMDAS and we'll get it all situated. So this is going to be, you can distribute. So looking at the first guy, I'm going to distribute the 5 times 10 over 19, and then I'm also going to distribute my negative Z times 10 over 19 as well. And I'll do that to each one. So I'm going to, right now I have 3 terms. I'm going to end up with 6 after I do this. So I'm going to have 5 times 10 over 19 minus Z times 10 over 19. All right, so that was the first guy. I just expanded that. All right, and then I'm going to have 10 times 7 over 19 minus Z times 7 over 19. So that was the second guy. I just expanded that. And then lastly, I'm going to have 20 times 2 over 19 minus Z times 2 over 19. And that was my third guy, and I expanded that. So now what I want to do is I want to group all the things that have Z, I want to group them together, and then all the things that don't have Z, I'll group those together. So I'm going to do that. So 5 times 10 over 19, that's going to be 50 over 19. So I'll show you what I'm going to do. I'm going to do these guys. Number only, number only, number only, and I'm going to put them here, here, and here. And then I'm going to go back and I'm going to get the Z stuff. Okay, so the next one is 10 times 7 over 19. So that's going to give me 70, which is 10 times 7 over 19. And then I'm also going to have 2 times 20. So I'm going to have plus 40 over 19, right? So those are the 3 things that I needed. Okay, so now that I've done that, great. I want to go back and I want to get my Z stuff. So I got to get all of these. And I'm going to put those right here. Boom, boom, boom. And there's really nothing I can do with those because, you know, except write 7Z and whatever, and 10Z and 2Z. But so I have minus 10Z, right? Multiply my denominator, my numerators, right? Because it's really Z over 1, minus 10Z over 19, minus 7Z over 19, minus 2Z over 19. And in order to make this a fair game, this has to be equal to 0. So for a fair game, we need the expected value or the mean to equal 0. So I'm going to end up with this equation here where it says 0 equals, and then I'm going to combine all my numbers together. Let's see what I get, right? Like I want all of these together now. So 50 plus 70. Oh, I think I've already made, oh no, that's right. 50 plus 70 plus 40, right? So that's going to be 160 over 19. And I actually can now combine my Z's together. So 10 minus 10Z minus 7Z minus 2Z, that's going to give me minus 19Z. So now I have minus 19Z over Z. And right, so those were my yellow guys here and the purple up here. There's something that's happening. Notice that I ended up with 19Z. That's not a coincidence. It's the same as the denominator, which that's on purpose. So I can actually go ahead and cancel that out. right? And then so what I'm going to have is that 0 equals 160 over 19 minus z. And I want to solve this equation for z. So I'm going to add it to both sides. So if I put 160 over 19 in my calculator, I get 8.42. So what this is telling us is that the game should cost, after we round, it should cost 8.42 to play. So think about it. If it costs 8.42 to play, if you pull out a $5 bill, you've lost money. You've lost $3.42. That's going to happen more than half the time because there's 10 out of 19 bills. But if you pull out a $10 bill, you're going to win $1.58. And if you pull out a $20 bill, you're going to win $11.58. So there's two bills that you're going to win at, and then there's one bill that you're going to lose at. The loser bills, the $5 bills, there's a lot more of those, right? Let's just look really quickly at Excel and see how it compares when we put this in. All right, so if it cost $8.42, and remind you that we rounded that. 160 over 19 goes on and on. $8.42, that's a rounding. So we're gonna see a little bit of a rounding error here at the end. So let's think about it. If we win $5, but it cost us $8.42, then in total, by grabbing that $5 bill, we actually lose $3.42, as we just said. If I pull out a $10 bill, but it's cost me $8.42, I'm only up $1.58, right? And then similarly, if I were to pull out a 20, well, I'm still out that $8.42, so I'm only gonna have $11.58 winnings. And if I put that in, notice what our mean is. It ends up being 0.001053. Now, in theory, we solved it so it's exactly 0. But what we did is we rounded the 160 over 19. So just to be extra clear on what the point I'm making is, if I change this to 160 over 19, and I change this to 160 over 19, and I change this to 160 over 19, then you see we get a perfect 0 mean. But, I don't know how to make change for, 57.89 cents. So I'm going to round it up. It's money. So there's a rounding issue. But the answer should be $8.42. If that's how much we charge to play this game, then it becomes a fair game.